is what you would end up with, saying that at 500 nanometers, this is the amount of energy that I'm going to sense. Now, of course, the same thing applies in terms of transmittance, right? So, if you're looking at this in a imaging modality, like where the images are formed because of not reflectance of the energy, but transmittance of the energy, so amount of energy actually absorbed by the object, then the same principles still apply. Nothing changes. Except that now you will have what you may consider a transmittance profile for the object. The amount of energy that's actually absorbed, or the inverse of that is being represented, the amount of energy that would be transmitted through the object. Okay. Now, we can actually go and say, if this is how color is represented, then obviously the color of what we consider semantic objects may not be a single value. Right? So obviously it's some kind of a profile. It's a curve over the wavelength space. So what is the color, let's say, of sky? And if we measure this under different conditions, what we find is that the color will be represented by all the different curves. Right? So on a cloudless sky, just before sunset, this is the kind of color that you would perceive. This is the curve that you would perceive on a cloudless sky at sunset. The bright snow and visible gray skies, or sun behind the cloud, and so on. So obviously you can see that the color perception is changing, not because the sky is changing, but because illumination energy is different, or for the matter, the radiosity is actually different. What we are perceiving in the camera, because of all the properties that we have talked about so far, right? Shadowing, interreflections, and so on and so forth. We basically have a constant illumination source in this case, right, which has a spectral profile, obviously. You have the same object that you're sensing, but the color that you will sense will be different because of the global illumination effects. Right? Different objects interacting in different ways, the different amount of light getting absorbed, and so on and so forth. Now, we can do the same thing in terms of illuminance, right? Different sources of light. So, for example, I may have a particular illuminant which may have a light profile or a spectral profile that looks like that, a red color. But I may take another illuminant and it may have a completely different profile. So now one can go back and say that, well, why do I sense different colors? It may be because the object is exactly the same, but the illuminant is changing. Because remember, the color that we are sensing is the illuminant multiplied by the property of how the object will react to light. So some reflectance property, let's say, of the object. So if the object is the same, nothing else is changing, just the illuminant is changing, obviously we're going to see a change in color. So this can become quite problematic, right? Because for most imaging conditions, neither do we have a good idea on what my color of the illuminant is, neither do I know the property or the reflectance property of the object. So what do I do with color information that I pick up? How do I trace it back? So one thing that we have talked about in the past is albedo, right? Albedo as a property of the object. So now, in terms of color, we can talk about spectral albedos. Right? What is the spectral albedo of an object? And again, we can now start generating albedo curves for different objects. So these are for different leaves, for example. These are different leaves that are different plants and so on and so forth. And each one has a spectral albedo. Now, if I know the spectral albedo of something, then now I have an ability to establish some relationship between different illuminants and what I sense. Now, for practical purposes, and certainly in the world of digital reproductions, we have tried to standardize the way we depict colors. Right? And most of these, you can think of them as cartoon spectra that we have designed. Right? So if you go and say, what is red, green, and blue? Right? Most of the time when you work with digital data, images, for example, they will have values and intensity values represented as red, green, and blue values. Right? Now, what are those? In reality, we have kind of designed these to be these cartoon values in the sense that everything between 400 and 500 will call blue, 500 and 600 is green, and 600 and 700 is red. On the other hand, you also have, mostly in print reproductions, you use rather than edited model, a subtractive model, giving colors such as cyan, magenta, and yellow, which are these particular corresponding blocks. So magenta would be a combination of blue and red in this particular case. So the RGB model that we typically use is what is known as an additive color mixing model, which means that we have defined these as independent models, but you actually can add the two spectra to realize a new color. So for example, red and green mixed together gives you yellow, where yellow is now this particular 500 to 700. And these are what we typically use for like monitors and in order to generate colors and so on and so forth. All additive mixing. For print production, on the other hand, we use more subtractive models or multiplicative mixing. Okay? So where you basically are looking at, let's say, a combination of cyan and yellow, which gives you green. Which is, if you do that, basically you're finding the union or the intersection. Like you find the intersection and you end up with the corresponding bracket and then it comes.
How is the rise in practice? How is this model actually realized in practice?
You are actually doing a point by point because you are using these colors, right? Natural dyes, I guess. And basically you are knowing the dye, and if you want green, you will add equal quantities of this and this. So that's how you realize a color. Right? And every color that you have is some discrete bucket. And what you are doing is adding the equivalent values in order to maintain that particular discrete bucket. So if I want, let's say, a color that besides here, then you will basically add this and this in amounts that give you that much residue. Now, keep in mind, and it's one of the reasons, the question is how do I get the residual, how do I negate the rest? That's why in printers, you actually don't just rely on cyan, magenta, and yellow, you actually have black. Black is what you actually use in order to suppress the residue.
You just take the fact that you're still adding the cyan there.
Yes. Yes. Oh, yes. Yes. Yeah. So now, of course, this is fine in terms of qualitative reproduction. Right? For us, that doesn't work. I mean, we are going to use these things somehow to compute, quantify what we are perceiving in an image. Right? So we want quantitative information coming out. So how do we specify the color in terms of numerical values? Because keep in mind, I mean, numerical values are important. A lot of times we'll go and specify colors and say, well, this is exactly what I want. Right? So if my ability to sense something is not quite there, then how do I use color in terms of descriptions? And also, colors are semantic labels will change not only from person to person, but even culturally, certain semantic labels change. Across cultures in general, maybe the common